This module will cover aerodynamics of the whole aircraft. Up to this point, we have considered only airfoils and finite wings. With these fundamentals in place, we can now look at the whole aircraft. We have defined the lift coefficient in previous discussions. Now, however, we will concern ourselves with the lift coefficient for the entire airplane. This includes the contributions not only from the wing, but also the fuselage, the horizontal tail, strakes, the vertical tails, etc. Practically speaking, in order to calculate an aircraft lift coefficient, there are three approaches which can be used depending on the known conditions of the problem. First, you can calculate it directly using the equations above. However, equivalent airspeed and weight must be known. Second, you could use the lift curve of actual aircraft test data. The lift curve must be available either from wind tunnel or flight tests, and the angle of attack must be known. Not all aircraft have instruments to measure angle of attack. And third, you could use the special relationship between induced drag and parasite drag for a known optimum performance condition. For example, if you're flying at L/D max, it can be shown that induced drag is equal to parasite drag. The aircraft drag polar, however, must be known. We covered high lift devices in the previous module. They are used to increase CL max. So it only makes sense that whole aircraft lift curves will change depending on the flap configuration. And here's some examples for the T-38. There are four basic types of drag: skin friction, pressure, wave, and induced. However, when discussing the whole aircraft, bookkeeping each of these becomes difficult. Therefore, in order to simplify the math, whole aircraft drag is divided into three main components. First, drag due to lift. Second, drag not due to lift. And third, drag due to Mach effects. Drag that is independent of lift is called parasite drag. Its corresponding coefficient is the parasite drag coefficient. Parasite drag includes skin friction drag and some pressure drag. It also includes something called interference drag, which is really just pressure drag due to component interference. Drag due to lift is called induced drag. Its corresponding coefficient is the induced drag coefficient. Induced drag for an airplane contains both the true induced drag from downwash due to wingtip vortices and some pressure drag, since pressure drag is a function of angle of attack. Finally, wave drag, which is due to shock waves and Mach effects. Interference drag is generated when several objects are placed in the same airstream, creating eddy currents, turbulence, or restrictions to smooth flow. For example, the air flowing along the fuselage collides with the air flowing over the wing in the area of the wing root. The effects of this collision can be reduced by allowing a smoother merging of two air currents by installing a fairing at the fuselage wing root junction. If an external store is hung on the wing of an aircraft and the drag of the aircraft and that of the store are known, the drag actually produced is greater than the sum of the drag of the individual components because of the interference drag. Anytime two parts of an aircraft are joined or any object is placed on or in close proximity to an aircraft, interference drag is created. In some cases, however, overall drag can actually be reduced by proper streamlining of the flow. An example of this beneficial effect is evidenced by the addition of the conformal tanks on the F-15. We've seen the diagram on the left in previous module. When the flight velocity is greater than the critical Mach, the drag coefficient increases. Below critical Mach, the low speed polar is fairly unchanged. Critical Mach is where the flow reaches sonic somewhere on the wing and a normal shock wave starts to form. After the critical Mach is exceeded, then a sudden increase in drag coefficient called drag divergence is experienced. Beyond Mach 1, the drag reduces, but not to the level prior to the critical Mach. Whole aircraft drag uses the equation CD equals CD naught plus CL squared over pi times E sub O times the aspect ratio. CD0 is the zero lift drag, which can be considered constant. Instead of the span-wise factor, Oswald's efficiency factor is used. We'll now describe these terms in more detail on the next slide. The zero lift or parasite drag, CD0, has all the constant drag contributions: all aircraft skin friction, pressure drag at zero lift, interference drag, and wave drag at high speed. All drag due to lift, CL squared over pi times Oswald efficiency factor times the aspect ratio, has all the variable drag contributions. And that includes vortex-induced drag, pressure drag that varies with lift, and any other drag that varies with lift. Since pi, Oswald's efficiency factor, and the aspect ratio are relatively fixed, the K term is defined as 1 over these values. The resulting equation, CD equals CD naught plus K times CL squared, is the mathematical equation for a parabola. Thus, people refer to graphs of CL versus CD as drag polars. Here's example drag polars for the F-16 at different Mach numbers. And as one would expect, there's higher values of drag at supersonic Mach numbers than subsonic Mach numbers. All somebody needs to generate a drag polar is a value for CD naught and the constant K. Some typical values are provided here. As we saw in the previous slide, these values will change with Mach number. Here's some typical values for UAVs. To find K from experimental data, simply plot CD versus CL squared. Then draw a straight line through the data. The y-intercept will be CD naught, and K will be the slope of the line. Here's an example showing drag divergence. Notice the curve is fairly flat or constant prior to about Mach 0.9. Here we show Oswald's efficiency factor is not really fixed. It does change with CL and Mach number. Drag changes from different configurations, or any lumps or bumps that we put on the aircraft, and we need to account for that. A term called drag counts is often used. One drag count amounts to 0.0001 of a drag coefficient. For example, a rocket launcher which increases the airplane's parasite drag coefficient by 0.0010 is said to have 10 drag counts. For external stores, flight manuals often use a drag number. A drag number is defined to be 10 times the change in drag coefficient times the wing area at a Mach number of 0.5. For example, if a centerline store has a drag number of 7, what's the corresponding change in drag coefficient if the wing area is 530 feet squared? The answer is 0.0013, which would be 13 drag counts. The equivalent flat plate area is a graphic way of expressing the parasite drag of a body. CD equals 0.003 has little significance to someone unfamiliar with the normal magnitude of bomb drag coefficients. It's similar to understanding values of Reynolds numbers. But an equivalent flat plate area of, say, 1 square foot has a definite physical significance. Until now, we have concentrated on the drag coefficient only, which is not a function of velocity. It is instructive to also consider the actual total drag, which is a function of velocity. It will be shown that in straight and level unaccelerated flight, that lift equals weight and thrust equals drag. Therefore, if we can represent drag in terms of velocity, we will know how much thrust is required to maintain straight and level unaccelerated flight. Recall that the total drag is composed of parasite drag and induced drag. A look at the drag equation is useful in understanding the shape of the drag or the thrust required curve. The first term is the parasite drag. The second term is the induced drag. And there's a few key points about the thrust required curve. First, parasite drag dominates at high velocities. Second, induced drag dominates at low velocities. Third, there's a velocity which will achieve the minimum drag possible for the aircraft with its given configuration, weight, and altitude. Minimum drag is given the symbol dmin. Note that since weight is equal to lift, then lift over drag is going to be weight over drag. Therefore, it's clear that L over D max occurs at dmin. Fourth, theoretically, the drag approaches infinity as velocity approaches 0. However, the aircraft is limited by its maximum lift coefficient. Therefore, the minimum speed attainable by an aircraft is vstall. The thrust required curve is therefore usually clipped at the stall velocity. Airplane performance is heavily dependent on the drag, or the thrust required curve, and the thrust available curve, which we'll cover when we get to engines. This chart shows that angle of attack and velocity are inversely related. Angle of attack is high at low air speeds and low at high air speeds. The drag, or the thrust required curve, will change with aircraft weight. As you might expect, the more an aircraft weighs, the more lift is required. Thus, lift-induced drag goes up, which is why the low speed side of the curve is impacted the most by a weight change. At really high speeds, parasite drag is basically unaffected, so the impacts of weight are minimal. Increasing altitude, which is the same as decreasing density, affects the thrust required curve by increasing the induced drag and decreasing the parasite drag. The net result is the whole curve shifts to the right. Notice the minimum drag is unchanged. It is a common misconception that drag goes down as you go up in altitude. This is really only true if you are flying faster than the velocity for minimum drag. In summary, the whole aircraft includes contributions from not only the wing, but the fuselage, the horizontal tail, the vertical tail, strakes, etc. Lift curves of actual test aircraft data are really the best. For drag, we saw the equation CD equals CD naught plus CL squared over pi times Oswald's efficiency factor times the aspect ratio. The zero lift or parasite drag has all the constant drag contributions, and that's all skin friction, pressure drag at zero lift, interference drag, and wave drag. All drag due to lift has all the variable drag contributions, and that includes vortex-induced drag, pressure drag that varies with lift, and any other drag that varies with lift.